Hello, Professor. This is Ritvik. Today I am going to present my midterm progress for my project called Steel Surface Defect Detection and Classification. The goal of my project is to automatically classify different types of steel surface defects using image processing techniques together with both traditional machine learning and deep learning models. For this project, I am using NEU Surface Defect Database, which contains 6 categories of steel surface defects commonly used for benchmarking defect classification algorithms. So now I will explain what I have completed so far. So in my project proposal, I plan to compare a traditional machine learning approach with a deep learning approach for classifying steel surface defects. During this midterm milestone, I focused on building main parts of the project. I first created a pre-processing pipeline for images to improve the quality of images. Then I developed a traditional H4G plus SVM classifier and a ResNet transfer learning model. Finally, I tested both models on same dataset and generated the initial results, which I will show in the next few slides. So before starting the implementation, I studied previous research on steel surface defect detection. Earlier methods mostly uses image features such as HOG, LBP, and GLCM together with machine learning models like SVM. More recent work uses deep learning models such as ResNet 50, which can learn image features automatically. Based on this research, I decided to compare the traditional HOG SVM model with the ResNet transfer learning model. And this comparison helped me understand how both methods perform on the same data set. So coming to the slide 4, the slide 4 shows image processing pipeline that I used throughout the project. So the first step is converting the images into grayscale because most of the dataset contains the grayscale images and this makes the processing consistent. Next, I will apply clay, which improves the contrast of the images, which makes it easier for us to detect the defect areas. After that, I apply Gaussian blur to reduce the small amounts of noise while keeping the important defect patterns. So finally, I use a canny edge directions to highlight the edges of the defects. These edges contain useful information that helps machine learning model distinguish between different defect types. So the pre-processing pipeline that I used is applied to all 1800 images in the dataset, and the processed images are later used for visualization and model training. So after completing the pre-processing pipeline, the next step was to build the classification model. So in this project, I implemented two different classification approaches so that I could compare a traditional machine learning model with a deep learning model. So the first model is the traditional HOG plus SVM classifier. So for this model, I extracted HOG features from the pre-processed grayscale images as well as the canny edge images. I then combined these features and used them to train the SVM classifier. And the second model is ResNet 50, which is a pre-trained deep learning model. So instead of the training the entire network from the scratch, I used the transfer learning. I kept most of the pre-trained layers and only fine-tuned the final layers for my 6 defect classes. And using these two different approaches allowed me to compare how traditional machine learning model and deep learning model perform on the same data set. After implementing both models, I trained them using the same dataset and compared their performances. The slide shows the results from the experiment performed during this time. The chart compares the performances of both the traditional machine learning model and the deep learning model using the raw images and pre-processed images. So starting with the HOG plus SVM model, we can see that the pre-processing pipeline improved the overall performances compared to the using the raw images. This shows that the improving the image quality before feature extraction helps the traditional machine learning model classify the defects more accurately. But looking at the ResNet 50 model, both input conditions achieve very high accuracy. However, the raw grayscale images perform slightly better than the custom pre-processed images in my experiments. Overall, these results suggest that the pre-processing provides a greater benefit for traditional HOG plus SVM model, while pre-trained SNET 50 model is already able to learn useful image features directly from the original images. So these findings provide a very good starting point for further experiments in the final phase of the project. So in this slide, we discuss about the key findings. So one of the most important findings from my experiment is that pre-processing affected the two models differently. So the HOG plus SVM model depends on the image features such as edges, shapes, and texture. Because pre-processing improves these image features, the model was able to achieve a better accuracy. On the other hand, the ResNet 50 automatically learns image features during its training. Since it already learns all these features on its own, additional pre-processing resulted in a slightly decrease in its performance and actually resulted in a lower accuracy when compared to the raw images. This comparison shows that the traditional machine learning model usually benefit more from pre-processing, while deep learning models are often able to learn useful features directly from the original images. So coming to slide 8, here we discuss about a few challenges I have faced while implementing the project. The first challenge was setting up the development environment and making sure all required libraries were installed correctly before I could train the ResNet 50 model. So another challenge was making sure that my pre-processing pipeline matched the method I had proposed in my project presentation. After reviewing my implementation, I updated the pipeline so that canny edge information was also included in HOG feature extraction process. I also noticed that the validation accuracy changed slightly during the training. So I carefully monitored the training process and selected the best performing model for my final evaluation. So coming to the last slide, here we discuss about the future work for my project. So for the final milestone, I plan to continue improving both the models. So I will perform additional parameter tuning and test different pre-processing techniques to see if the performance can be improved further. I also plan to implement GradCam visualization so that I can better understand which parts of the images are most important for the ResNet 50 predictions. And finally, I will compare all the experiment results and complete the final report and prepare the final presentation. Thank you.